All right, this is a quickly sketched sine curve, right? Sine starts at 0, goes up to 1, and then comes back down to 0 when you get to 180 degrees on the theta axis. And oops, this shouldn't be sine of x. This should be sine of theta. I'm too used to using x as a variable. Okay. But let's use theta because it's an angle, right? Um, and then it goes down to -1, and then it goes back up to at 360 degrees to a sine value, a y value of 0. So, two questions. First of all, what happens before the origin, and what happens after 360 degrees, right? In some sense, we go, you don't go, oh yeah, let's talk about 367 degrees. You don't kind of do that. You just go from 0 to 360. But the fact that you don't do it often doesn't mean you can't. 361 degrees is a perfectly fine measure of an angle. It's just really the same thing as 1 degree. In other words, the coterminal angles. So let me draw a slightly longer set of axes. So that's too long. That's going off the screen. There we go. We have this piece here. This is 360 degrees, and this is 0 degrees. And it goes up to 1, and it goes down to -1. So this is like a little piece. So this is like the piece of the sine graph that we had above, kind of put down, zoomed out, if you will, right? Now, the thing is, well, what happens after 360? Well, remember that if we think about unit circle, or you just think about standing there and spinning 360 degrees, you get back to where you started. So really, when you're here, that's the same thing as being here. So what comes after 360 degrees should be the exact same thing that comes after 0 degrees. And then we get to, well, okay, we go from 0 to 360, and then we go from 360, which is like the same thing as 0, another revolution, another rotation, that would be at 720. Then we'd be at 720 degrees. Then we can keep going for another 360 degrees. Then we can keep going and going and going. Just keeps going like that forever, right? That's why we call this a periodic function. To the left, remember that 0 is the same as 360 degrees. So, what comes before 0 degrees? Well, it's what comes before 360 degrees. It's like this, like kind of drawing the opposite one. And here is -360 degrees. And then it kind of just keeps going that way. It's like a wave that goes on and on forever on both sides. And what we really need is that one purple piece in the middle, and once we have that, we can just kind of copy paste it, right? To the left and to the right, and it's the same thing. We draw it once, we copy it for the other ones. And that's one reason why we just look at 0 to 360 most of the time, because if I have another angle like 2552 degrees or whatever it is, I find a coterminal angle of it by subtracting 360 enough times, and poof, I find its sine. I find it on a graph. I use a calculator on that or whatever. 0 to 360 is really, for in this case, the only thing that really matters. Once we have it, everything else is a copy of it. This is why we call this a period of the sine curve. It's sort of one piece. When we say a period, we mean that it's a piece that gets repeated again and 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 again. Keeps coming back. And to that end, because sine y equals sine of theta is a function that repeats itself, that repeats one period over and over again, we call it a periodic function. Just some terminology. While we're at it, let's add a little more terminology. the amplitude of y equals sine theta is 1. What that means is this kind of wave goes up to 1 and down to -1. That's all it does. It doesn't go to 2, doesn't go to 7, it goes up to 1, it goes down to -1. 1, -1, 1, -1. That's how far it goes. So I guess the total height is really 2 because you have 1 and -1, but we just want to kind of measure from the middle to the top. So we say the amplitude is 1. And just to make things a little more confusing, the period of y equals sine theta is 2 pi. So we use the word period to mean very many things, like the thing you put at the end of sentences. And here we say a period is sort of a chunk of the sine curve that gets repeated. Period, mathematically, we also really think as a number, it's the width of the piece that gets repeated. And we want to make sure that we use the smallest width because, we could always repeat 720 degrees. I meant 360 degrees. Those of you who already know radian measure will know why I put 2 pi in, because I'm kind of so too used to that. Really mean 360 degrees. Sorry. Okay. The piece of the sine curve that repeats itself, the one that I circled in blue here, is 360 degrees long horizontally. And so the period of this curve is 360 degrees. We could say it repeats every 720 degrees, but, since 720 is bigger than 360 and 360 works, we just say, let's use 360. It's like the lowest common denominator, lowest common multiple. So, you want a common multiple, let's use the smallest one. You want a period, you want a length of the repeating pattern. Let's figure out what the smallest repeating pattern is. Okay, so that's sine. Cosine is the same thing. I'm not going to do it. You can do it on your own. You draw a cosine curve from the beginning to the end. You can cheat by using arrows because you don't want to spend infinitely many time on this. Okay. So let's look at this one piece of sine that we said is important, right? 180, 360. 1 minus 1. Okay, so this is the sine curve, or this is one piece of the sine curve. Y equals sine of x. Let's do stuff to it. But let's do stuff to it, I mean, let's transform it. Let's make it y equals 2 sine x. Remember that multiplying the entire function by a number dilates it or expands it vertically by that number as a factor. So now this thing is going to be twice as tall. Both ways, right? Both up and down. So this is going to be at 2 and at -2. If I multiplied it by 0.5, it would shrink. If I multiply it by 3, it would get even bigger. One important thing to note is now the amplitude is equal to 2. Because not only are you going up to 1, you're going up to 2. Which makes sense because the function is twice as big now, vertically. Not a fun one. I'm going to use another color for this one. What if I do y equals sine 2x instead? Instead of doing y equals 2 sine x, let's do sine 2x. Let's multiply x by 2. Well, remember that this gives a horizontal dilation, but that dilation's not expansion, it's contraction. So it kind of shrinks in size. Instead of taking 360 degrees to go all the way up, down, and then up again, it's only going to take 180 degrees. which is kind of weird. But when you think about it, right, 2x, 2 times 180 is 360, so, 180 is now the new 360, I guess. And so we're actually contracting this function by a factor of 2. The amplitude is still 1, right? You only go up to 1, you don't go down to -1. But notice that the period is now only 180 degrees. It only takes 180 degrees to do that one sine wave piece. In fact, I can continue this, and you notice that there are two pieces from 0 to 160. Oh, sorry, from 0 to 360. Which makes sense, because if you squish it into half its original width, well, you can fit two of them in the original space. So, I guess a summary would be, if you dilate a sine function, the graph of a sine function vertically, you change the amplitude, you change how far up and down it goes. And if you dilate a sine curve horizontally by doing like 2x or 5x or whatever, you change the period. It takes less fewer or more degrees of angle, if you will, to get through that one up, down, up motion. And when you do that, you can possibly fit more or fewer even if you expand instead of contract. If you could fit more or fewer of these curves in a single 0 to 360 degree section.